in the Department of Mechanical Engineering, Walchand Institute of Technology, Solapur. In this session, we will see numericals on conduction through wall. Learning outcome. At the end of this session, students will be able to solve heat transfer numericals on wall. Now, numericals on conduction through wall. Till now we have seen the general heat conduction equation in the Cartesian coordinate system. So, in walls, so this will be conventional representation of the wall, where the wall material is represented by this hatching line. The thickness of this wall is L. The inner surface temperature is suppose T1, outer surface temperature is T2, and the rate of heat transfer is denoted by Q dot. The thermal conductivity of this wall will be represented by K. The unit of temperature is either degree Celsius or Kelvin. The heat transfer rate is in watt, length is in meter, and thermal conductivity is watt per meter Kelvin. Already we have seen all these notations. Now suppose inner surface temperature is 100 degree Celsius, outer surface temperature is 50 degree Celsius. Now the material of the wall is suppose stainless steel. Then the thermal conductivity of stainless steel is around 50 watt per meter Kelvin. Then calculate the rate of heat transfer. So this will be the given data. Immediately after given data, you are supposed to draw the thermal network. Now in the thermal network, there will be two nodes will be there. This is the temperature T1, this is the temperature T2. So here inner surface is represented by T1, outer surface is represented by T2. Then as per the electrical analogy, the thermal resistance is symbol for representing thermal resistance is this one. So the representation of thermal resistance is R suffix TH. This is thermal resistance. Unit of the thermal resistance is Kelvin per watt. So we know Fourier's law of conduction, that is Q is equal to Ka delta T by L, which can be written as delta T divided by L by Ka, which is also equal to delta T by R thermal. Now here they have asked us to find out the conductive heat transfer rate. Then rate of heat transfer is equal to, so here in the numerator delta T is the temperature difference. If you are taking temperature in degree Celsius or in Kelvin, the difference will be same. Okay, so as here the temperatures are in degree Celsius, I will take it, there is no problem for that. So what is this delta T? Delta T is T1 minus T2 divided by L by Ka. Remember, small k notation is used for thermal conductivity and capital K for temperature in Kelvin. Now substitute these values. So what is this? T1 is 100 minus 50. See here, this is the temperature difference. So either you take in degree Celsius or Kelvin, the difference will be same. Now here let the thickness of this wall is equal to 0.1 meter. 0.1 divided by thermal conductivity given is 50. Now in this numerical the area is not mentioned, so by default per unit area you will be calculating, that is nothing but heat flux. Okay, so per unit area is Q dot by A is equal to heat flux, where Q dot is equal to capital Q by capital A, which is known as heat flux, and the unit of heat flux will be watt per meter square. Per area per meter square, what is the rate of heat transfer? That is known as heat flux. Now if you solve this, you will get the rate of heat flux in watt per meter square, and its value is so if we substitute the values, then difference of numerator is 50, 0.1 divided by 50 is 0.002. You will get answer 25,000, that is watt per meter square, or 25 kilowatt per meter square. So this is the methodology of solving conductive heat transfer numericals for wall. Initially you are supposed to draw the schematic sketch followed by given data, then draw the thermal network. After the thermal network, the required relation, as this is the conduction, we should use the Fourier's law of heat conduction, substitute the values and you will get the answer. So put here answer. Okay, this was the first numerical. Now similarly, if there will be two walls, this is the wall A, this is the wall B, and these materials are different. A and B, two different materials are there, having their thermal conductivities Ka, Kb. Inner surface temperature is T1, outer surface temperature is T2, and the interface temperature is suppose T3. The rate of heat conduction is Q dot. The respective thicknesses are L1 and L2. Now see here, before writing the given data, we will draw the thermal network for this. So for this is known as composite wall. In first case plain wall was given, now here two walls means composite wall, and the thermal network will be first temperature, inner surface temperature is T1 given, interface temperature is T3, and outermost temperature is T2. This will be the resistance of A, this is the resistance offered by B material. Now after drawing this thermal network for this composite wall, the Fourier's law of heat conduction, Q will be equal to, now see here, T1 minus T2, you should take T1 minus T2. So T1 minus T2 divided by Now here two resistances are there. So what is the use of thermal network? It makes the numericals simple. So just add this, that is Ra plus Rb, which will be equal to T1 minus T2 divided by R total. Now for steady state condition, and if the walls are in series, this is the case of series, walls in series, Q will be equal to Q1 is equal to Q2. Means if you want to find the interface temperature, that is T3, then we can write the Fourier's law of heat conduction like Q1 is equal to, Q1 is flowing through first wall, so that is T1 and T3. So I can write T1 minus T3. Now here which resistance will come? Yes, it is only Ra. Now see here, Q is equal to Q1, which is equal to Q. So already we know this Q value. So you can substitute over here. T1 is known, Ra already calculated, unknown T3, we will get the value of T3 either in degree Celsius or in Kelvin. So in this fashion you can solve the numericals on plain wall and composite wall. For more references, you can have heat transfer by Yunus Sengel Microhill publication. Thank you.